and technology. Oops, now the clicker has stopped its live, so maybe just click on the slide, that would be nice. So we just go to the next slide. Oh, here it works. And before I'm handing over, it's always my pleasure, as being also one of the sponsoring chairs of this event since many years, to thank the sponsors, because without the sponsors, it would not be possible to make something, a show like this. So thanks a lot to all of our sponsors that are also on site. Speak with them. We have gold sponsors, the Dutch Cadastre, Ordina, Pull Party, Semantic Suite, and Texonic. We have silver sponsors that are OntoText, Oracle, and RWS. And finally, bronze sponsors and startup sponsors that are Enterprise Knowledge, Oxford Semantic Technologies, the QA company in Tripoli. What is nice, it's US, it's UK, it's France, and it's the Netherlands. So you also see how international this conference has become over the last years. Nevertheless, have fun, enjoy these days, and I will hand over to Victor as a next step with a clicker and a microphone. Thank you.
Thanks so much, Martin, and welcome everybody here, and also now welcome everybody online, because we had some technical challenges that you weren't aware of, but now the online people join us. So if you see camera, wave, and they can join us online. So yeah, it's up to me to tell you a little bit about the rules of the game. Of course, we're not in a normal year. We had to postpone it, Semantics 2020, to this year. We're very glad that we can have you now, but this comes with a few rules, and they both involve hygiene. One is about Zoom hygiene, and the second is about real hygiene. So anyway, first of all, it's just some sort of regular conference hygiene. Please stick to schedule if you're presenting, and yeah, we have a lot of sessions. People would like to move between sessions, so yeah, let's try to make that possible. There's pointers to who you can talk to in case there's a challenge with a hybrid setup. Then for the online presenters, yeah, you should all have received a Zoom link that you can join. Please join a bit ahead of time, so if there are any challenges, you can solve them with your session hosts live. Yeah, the rest is, I think, by now common Zoom hygiene, right? So we saw in the morning in the workshop sessions that you've all now have worked with Zoom at least once in the last 2 years, and this seems to work well. For on-site presenters, so those of you who have not done that might have sort of forgotten how to do that, but also it's a good idea to be in the room roughly 50 minutes before, so you can set up and talk a bit about the hybrid setup, because it's not a completely business as usual setup. To make it work, we need to make sure that everything is playing by our complex rules, so please be there. You get a microphone and the clicker, so actually this seems to work well. And then, yeah, if you have any challenges, there's some links and email addresses that you can go to. Then the fun part, tomorrow we have a dinner. Dinner will actually be hosted here, also because of COVID regulations. We cannot go too wild, but let's make it wild here in the Meervaart. So the dinner is tomorrow from 7 on, but you have to register. So if you haven't done so, please do so now or quickly after this talk, and you can do it on the website. And then, of course, we are here under strict Dutch government regulations. Unfortunately, once you're in, it's more or less okay, right? So we are all checked at the gate, which means that the green pass rules have applied. And just that means that if you are able to sit down during a talk, please do so. So we are one of those placed events. And there's hand sanitizers everywhere. And if there are any additional requests from the Meervaart people, please follow them. So those are the rules, but now let's talk about what we're actually doing here. So we have a very nice mix of talks. Oh, 6:30, the conference dinner. I was just we just moved ahead to a more Dutch time, I guess. 6:30 is good. Anyway, so yeah, we have. I think Semantics prouds itself to have a very mixed type of talk. So we always have mixed research talks, research and innovation talks with industry talks. And so that's reflected in the research and the industry track. For the research track, we had more than 60 submissions, and with an acceptance rate of 28%, I think we're a nice and competitive academic conference. And then for the industry track, we have 24 accepted talks. So that's a nice mix between research and industry talks, and they're mixed in the program. So you will see them exchange seats, basically. And both follow the very nice quality control mechanisms. And then also we have a poster and demo session. So there's posters here on the top floor. Some posters will be presented only digitally, and some will be presented online, on site. Then a special mention for the special tracks or the special subtopics for which we have specific program committees. So digital humanities and cultural heritage makes a comeback, as does legal tech. So look in the program for those tracks if you like those topics. And then there's a special one, the German Society of Knowledge Management hosts a session tomorrow. So all of these are clearly marked in the program. So conferences do awards, and we do them as well. We do them well, I think. So for the research and innovation track, the program committee has selected 3 papers. The program committee just walks in the room. And then the selected papers are shown here. So these are, let's say, hidden recommendations. If you want to look at a nice paper and you don't know what to go for one of these. And the decision will be made also on the basis of the presentation, right? So it's not decided yet. We will decide before Wednesday, 6 o'clock, when the award ceremony will start. So for the poster and demo session, something similar will happen, but these were selected, of course, by the poster and demo track chairs. So again, some of these posters are online and some of them are on site. So please go to the Minute Madness, which is tomorrow. To watch the videos, the 1 Minute Madness videos of the posters, and try to look at the posters while you're having your coffee or sandwich. And for the industry track, we also have nominees of best presentations. And again, these will also be judged on the basis of the presentations themselves. So do your best. Yeah, then a quick word about the proceedings. So all of these links are online. The proceedings came online, I think, last weekend. So you can actually, all the papers are published as open access papers, so you can just read them and share them and comment on them as much as you want. The poster and demo proceedings were, I think the URL just appeared, so they might not be online as we speak, but they will appear during the conference. So just hit that F5 button as much as you can. And the workshop proceedings will appear later on. So there's the workshops do their own proceedings. And of course, they're collecting material as we speak. Again, all the links, you don't have to type them over. They're on the website. Then, ahead of the closing ceremony, where we spend some more time, a big thanks to everybody who made this possible, including the organization chairs, the program chairs for the different tracks, but also the local organization who did a great job in making this complex hybrid puzzle sort of work so far, right? So very happy that this is working. And a very special thanks to all the volunteers that you see walking around in the gray t-shirts. Again, if you have a question, don't hesitate to stop them. And of course, this would never have been possible without, first of all, the organizational partners of Semantics who are shown on top, but also we're very, very grateful for this year that you are such nice sponsors for us, all the sponsors that made this financially possible. And then, of course, special thanks to you. I think the first thing everybody says to me when they see me is, wow, this is so nice. People again, right? They actually exist, and you exist from the waist down as well. So I'm just glad to see that you are as tall as I remember you, or even taller. So that's it for me. I will hand over to, which is not the keynote speech, but actually a welcome talk. We're very glad to have him here. And we just figured out this was the third attempt at getting Ger Baron to speak. He was invited for 2017 when Semantics came to Amsterdam for the first time. Then he had other important business. I forgot what it was. It was the birth of his child. So, okay, fair enough. And then, last year there was something else why we couldn't do it, something with a disease or something. Anyway, good reasons. But now he finally is here. So I'm very happy to give the floor to Ger Baron, the Chief Technology Officer of Amsterdam, who will welcome us to this wonderful city.
Thank you. And thanks for the third opportunity to be here. Yeah, so welcome everybody. Welcome to Amsterdam, obviously, to well, our city, which is actually last year changed quite a bit, I would say. I mean, Corona has a big impact on cities nowadays. You have all these pictures of empty cities. Probably you know it from your own city as well, basically. So we're well, it's interesting times to work for a city, basically, because we now need to do all types of other things. We need to manage public space for health, like sanitizing stuff, etc., keeping distance, etc. So we got all this new stuff coming to us. But even more, I mean, and this conference, and I realized being over here that and talking to the organizers before, basically, that actually it's a shame that we don't do more together, basically, because the stuff you do actually is probably more relevant to a city than ever. When you look at the stuff we do, I mean, the data we have nowadays, the data sharing programs we do, varying from well, CBS or Cadastre or WS, but also to Uber, Airbnb, or all types of other data initiatives, citizen science initiatives, and we collect all this data, and we actually don't have a clue to do what to do with it. What happens in the city is that we make graphs, and then it has a number. So our city is clean 28 today. People are happy 23. And I'm not even joking. I have this graph on a daily basis on how are we doing, basically. And nobody really understands the meaning of it anymore. So we collect all this data from our assets, but also from texts, from social, etc. But we don't have a clue what to do with it, to be frank. We get all this graph and we think we have insight what happens into a city, and then we still don't have a clue because we know that it's 28 clean. But are we happy with 28 clean? Yes or no? Is it good to be 28 clean, whatever? We don't know. So the abstract fallacy actually comes to us more and more, basically, because we collect more data, big data, make more connections, all types of people who have their own definitions of our own of the data, what we have, even the definition of what's a neighbor. We're organizing try to involve some people in moving this building actually in this neighborhood, which people who read local newspapers have noticed we did not very, well, I would say correct. Well, my deputy mayor would probably say it's correct, but we did very well. We did it correct, obviously, because civil servants, but it didn't, well, people weren't very satisfied with the participation progress around it. But all these things, what's the definition of a neighbor? So we put a neighbor, what's a neighbor? It's an interesting question. We could discuss this for hours. Is it somebody who lives there half of the time or full time? Or when you hire out your house for Airbnb, is this a neighbor, or is it for half a year or a year? So even a simple thing, what's a neighbor? We don't have a clue actually anymore. So to put and then comes all the asset management, obviously, where you talk about as well, and then what's functional, what's not functional, how can we interact with all these things together? Basically, the city as a platform is something I've been hearing from also Vanessa from IBM is talking about 2008. IBM started the Smarter World program with big control rooms, everything. Talking to everybody, and the mayor would control the whole city, red button and everything, basically. But I mean, well, we're happy that the traffic lights still work actually sometimes. So it's because they work on a communication protocol. I think it was 1979 or something, and then we come up with all these new things on top, and we don't have a clue. So we really need to rethink the way we look at the city and put a layer on top of it where we actually start to understand what's happening in the city. And well, the discussions you're having, the research you're doing, the work you're doing, actually, I would say would be more and more important for us as a city. So after this conference, I will contact the organizers as well to see how we could actually get more collaboration on this as well, because semantics for cities actually would be a very nice topic to talk more about and work more about. So, well, a lot of words, basically. What I'm trying to say is great that you're all here, basically. And it's not only that I'm saying this because we love conferences in the city, and it's great that we have physical events again, and we hope that you spend a lot of time drinking beers and go to restaurants, etc. Obviously, we do that as well. But also, it's great you're on this topic, which is more relevant for us than ever, basically, and maybe many more other topics. Because for us, understanding what's happening in the city, physically, socially, economically, starts with understanding what's happening in the city, and these other things actually you know more about than we do. So hopefully we next time when this be in Amsterdam, we could also present the results of the Semantics for Cities, I would say, program, which maybe we could start talking about. So thanks for being here. Hopefully, well, probably read your successes in your posters later on, basically, but hopefully this will be very relevant for you, and I'm sure it will be relevant for us as well. Thank you.
Thank you, Herr, for this very nice introductory talk. Yes, and now we see what the hybrid setups brings, what kind of circumstances it brings about. We have to stick to schedule, and Enrico's talk is scheduled for 1400. So we have a very short break of 9 minutes. We will have to be honest, we have to get Enrico into the room. He will be presenting online, and we are just about to do this. So stay on your places, on your seats, or get some refreshments. We'll be back at 1400 sharply. Thank you.
1.1 What do you mean? Guys, can you hear me?
Hello, Enrico. We can see you now. We just cannot hear you yet.
Can you hear me now?
Yes, I can hear you. So it is from our side that you're not amplified yet. Jullie moeten hem nog versterken,
kan
want
niet
ik hoor hem.
tegelijkertijd, dan zou die echo. We hebben nu en unmute staan. En als we dan ook al zijn audio horen, dan gaat het echo.
Nee, het gaat niet echoen. Want Zoom die trekt dat.
Hoe kunnen wij
Do you still get a echo?
No, not no, not. We have to unmute you still on the sound system. I can hear you, but
If I can always use headphones, but normally I don't.
it should be okay. No, that is not a problem. Ja. We moeten het kanaal unmuten. Can you say something, Enrico?
Hello, can you say something? Amsterdam. Good afternoon, Amsterdam.
Available now. Maybe if you can put your headphones on.
Okay, that will require 1 minute.
Okay, Enrico, we wait for 2 minutes.
Okay, can you now hear me?
Enrico, we can hear you. Nice to have you here.
Okay,
You're already on broadcast, so we can see you, we can hear you. We have a very strict paradigm. We need to stick to the schedule, so we will start in exactly 1 minute.
Okay, yeah, as long as you can hear me fine. Yeah, your sound is a little bit on the. Sorry, can you speak again?
Yes. One more rehearsal. Can you hear me? Can you understand me? You are live.
Yeah, that's fine. Yeah, that's loud enough. Yeah.
Perfect. Thank you.
Okay, so ready. So I'll go when you tell me to go.
Yes, 30 seconds more and we are ready to go.
Okay.
But I think I can use the time to say once again, hello to everybody. Great to have you here, either online or on site. One important thing that we need to share with the people participating online, please mute yourself. We have let's say, we have tried to make the online setup as easy and simple as possible and not to hassle around with admin rights and similar. So just to keep it short, please mute yourself. If you have questions, please write them into the chat. If you're online, of course, if you're on site, you can pose your questions after the talk. And yeah, and now I think we can start. Enrico, it's great to see you. It's great to hear you. Great that you are here. And I want to give you a brief introduction for all those who are not that familiar with Enrico's work and who he is, where he comes from, what he's working on. So Enrico leads the Intelligent Systems and Data Science group at the Knowledge Media Institute of the Open University in UK. This is also the reason why I unfortunately can't be with us here on site, because travel restrictions from UK are really, really strict. But for me, it's a really, really big pleasure and honor to introduce Enrico here, because he's probably one of those founding figures of the semantic web, or to say it differently, if there wouldn't have been Enrico, the semantic web would not be there where it is today, also with all these further developments that we saw as springing off from the semantic web as an idea, as a technological concept. So he's basically working at the intersection of language, logics, and especially also, as we will see in this talk, how actually we can combine and converge various systems like language-based system, logic-based system with machine learning. What is also very specific about Enrico, he always had a very user-friendly approach or user-centric approach. I first got in contact with the idea of the semantic web around the year 2002, and then in 2003, something appeared. Maybe some of you still remember the Magpie browser, the first RDF browser that was there in place, that should make it simply easier to access RDF data, to browse this data, to reuse this data. But as I said before, I think one of Enrico's specialities is to think in terms of convergence. So how can we bring the various technologies and systems together to that there exists a good interplay, so that we can benefit from the promises that are in the technology. And today he will talk about a topic that also shows us where actually the things are going, where semantics is unfolding. And it's about combining deep learning and common sense reasoning in visually intelligent robots. So give a warm hand to Enrico, and Enrico, we are very eager on your talk.
Okay, thank you very much for the extremely warm introduction. I really appreciate that. And let me say first how immensely frustrating it is not to be there in person. But yeah, I'll try to do my best and you know, convey as much presence as Zoom allows. I always like to have a little bit of interactivity when I give a presentation. So, but of course, it's a bit difficult for me to monitor the chat box. So if the organizers can help me with that in case there are questions, I'm happy to be interrupted. And also sometimes I may ask questions to the audience, so I'm happy for somebody to convey the answer to me. So let's see how it goes. I'm going to talk a little bit about this work we are doing on visual intelligent robots, and so to make it more concrete, I will use a very precise scenario, which is one of a robot which is called Hans, whose job is to ensure that the health and safety guidelines applicable typically to any department, the Open University, including our lab, are not violated. And this basically, from I would say, from a broader artificial intelligence point of view, essentially we are talking about primarily here visual intelligence. Essentially, we want to have a robot that is able to go around the lab and understand the world in front of it. And of course, this world is very dynamic because objects are moved all the time, people move all the time. Things, even the layout may change. So basically, we feel that this is really a nice concrete test case to study visual intelligence in general, and also to study a particular specific class of what we call service robotics. So in general, when we talk about service robotics, we talk about robots who are able to act autonomously, or sometimes semi-autonomously in the real world, to perform tasks that we normally say require a certain degree of intelligence, like being a waiter in a restaurant that requires the ability to to interact with the customer and then bring the right order to the right people. But also things, for example, during the COVID pandemic, there have been some experiments with robots in healthcare, because of course, one of the key elements of service robotics is the fact that there are many situations where it may be dangerous for human beings to perform tasks. And of course, if we can develop robots that can perform tasks in those situations, like for example, when taking measurements from a COVID patient with the same level of performance as a human being, that's of course very useful. My final example is, if you look here on the bottom right corner, you can see an example of these delivery robots, which are now being used in Milton Keynes, deployed in Milton Keynes for now about 2 years. And these are delivery robots. You order something from a supermarket, and this little autonomous robot come to your place and delivers. And the interesting thing is that this will sound like science fiction until not that long ago. And now, after 2 years, everybody in the city has got used to just see robots going around, which is actually an interesting example of how people they get, how ordinary people get very used to technology developments, which may have seemed quite far-fetched, as I say, not that long ago. So let's go back to Hans then. By the way, if anybody can think why Hans is called Hans, he can write it in the chat. And the first person will get an acknowledgement from me or from the organizers. Let's see a concrete example in which essentially you have Hans doing his routine investigation. He goes in the printer room, and in the printer room we have a number of objects. We have cupboards, but also on top of these cupboards we have a portable heater and a pile of paper. So essentially, what we want Hans to do is to recognize that this is a violation of health and safety guidelines. That is, a portable heater should not really be on a pile of paper, because a portable heater is an electric device, and the electric device, of course, can overheat. Paper is flammable, and therefore that is a flagrant violation of health and safety guidelines. Now, the interesting thing so this all, by the way, congratulations to Nina, was the first one who got it right. Yeah, Hans is health and safety. Is a very clever pun on the health and safety acronym. So, so basically, as I say, this is something that any human being can do very easily. But actually, if you start decomposing it in the various epistemological capabilities that you need, actually is not trivial at all. Of course, first of all, you need to have a knowledge of health and safety rules, which of course can be reasonably complicated or reasonably vague, because they talk about generic objects. They don't necessarily talk about an electric heater or a pile of paper. But for example, they may say that essentially electric appliances cannot be situated close to flammable material. Then you need, crucially, you need to be able to identify objects in the world. And of course, the real world is a little bit different from a lot of the, for example, image recognition benchmarks that are, tend to be a little bit sanitized. If you look at the example of a robot going in the printer room, where the electric heater could be on top of the cupboard, so from a completely different viewpoint from where the robot is, could be on the floor. Of course, you have light coming from the window, and you can have a sunny day, you can have a rainy day, and the light, objects will look very different. So is actually, the real world is very dynamic, and even object recognition in a very dynamic world becomes a lot more complicated. And then, of course, you need to have a lot of domain knowledge. You need to understand the properties of electric heaters and papers. And then, more interestingly, that's where common sense starts to get in the picture. You need to understand spatial relations. For us, it is obvious to say, yeah, the heater is on top of the pile of paper. But what does that mean? For example, we understand that if the heater is on top of the pile of paper, is touching the pile of paper, unless it is suspended from the ceiling, which would be quite unusual. while a robot, needs to compile all these common sense knowledge, which is not trivial. So in particular, essentially the point is that we can very easily, from a sentence like the heat is on top of the pile of paper, we can quickly understand exactly what's going on. In particular, the two things are touching, while, for example, and in particular, we understand that it's not just being above, but is on, that is being above and also touching. And of course, this is not the full list. There may be other capabilities that are required, and indeed, I will introduce some of them later on in the talk. But essentially, the point of this introduction is to say, this is not at all a trivial task for Hans to do. So essentially, the research goal, which we started this line of research a few years ago, is okay. How can we go about equipping Hans with the required level of visual intelligence? So I will do a tiny digression on architecture for artificial intelligence. In the sense that, of course, the example I'm talking about building an intelligent sort of health and safety manager is just a concrete instance of the generic problem for AI, that is to build intelligent machines. As Newell and Simon, or Newell, Shaw, and Simon pointed out in 58, AI is not about talking about intelligence, it's not about theory of intelligence, it's about operational theory of intelligence, it's about what they call the synthetic approach to intelligence. And of course, over the past 60 years, we have had huge amount of research, and different paradigms have been proposed, from the original general problem solving of Newell and Simon to expert systems in the 80s, knowledge-based systems, and then in the 90s, especially, there was the development of large-scale ontologies, and of course, nowadays the dominant paradigms tend to be neural networks, and of course, again, this is not an exhaustive list. So, as I say, I'll do here a quick digression. So essentially, the original AI paradigm was the one defined by Newell, Shaw, and Simon, which see AI as search. And indeed, a lot of people even today will say that the difference between AI and other types of computer science algorithms is essentially that AI is about search. You can't just write an algorithm that follows a sequence of deterministic steps and reach a solution and say that AI, because essentially associated with AI is the ability to reason about multiple options in situations which you may not get it right. And of course, the search paradigm conceptually is very simple. You have states and you have operators to navigate these states. Like, for example, in the case of Newell and Simon, they worked on theorem proving. So essentially, you had a logical theory to start with, and then you have to try and find the solution to the proof for the theorem. And indeed, in my own PhD, I use the search paradigm as the main problem-solving architecture. But of course, by the time I was doing my PhD in the 90s, in the late 80s and 90s, the knowledge-based paradigm was I would say, the most important one. Therefore, my take on the search paradigm was much more knowledge intensive. For example, what Newell and Simon were talking about. So I was doing design problem solving, which meant to have task ontologies for design, characterization problem solving methods for design. So generic knowledge, generic ontology about design, as well as also a lot of domain specific knowledge about the domains I was tackling. For example, the benchmark elevator design, the VT elevator design problem. And indeed, this is because another key paradigms in AI is what is called the knowledge-based paradigm, which was best, I would say, formulated by Brian Smith back in 1982, when he said that essentially what we are talking about is this causal connection between having lots of knowledge about the world and an intelligent behavior. And of course, the side effect of all of these is that for the past 40 years, there's been lots and lots of work on developing these large-scale, I would say, knowledge resources. These large-scale knowledge bases that can power intelligent problem solving. Back in the 80s, there was the Psych project, which is actually still going 40 years later. Of course, nowadays we have a variety of resources that we can use to try and give our systems and our robots the required degree of intelligence, like DPpedia, but also, for example, more specific, for example, to the image recognition task, things like visual genome. So, and then, last but not least, when a lot of people nowadays, when they talk about AI, they really talk about the new deep learning architectures, which have shown to basically exhibit the level of performance, which is much, much superior to other ML approaches on a variety of tasks, which typically have to do with pattern recognition, like speech recognition, image recognition. And of course, given these, given the state of AI nowadays, given that, of course, object recognition is a key precondition for visual intelligence, it makes sense to consider deep learning as the starting paradigm. At the same time, it's also important to point out that although there's been a lot of success with this kind of architecture, they still are rather unsatisfactory in the sense that, you train a deep learner on a particular language, language recognition task, speech recognition task, you give enough data and eventually the performance will be phenomenal. But the reality is that, again, the real world in which Hans operates, in which objects can be seen from different positions, the light changes, objects are moved from one place to another, is much, is much more resistant to data-hungry training. You simply cannot solve the problem simply by providing more and more data, because there's just not enough regularity there. And so there is this, brittleness problem, which is, again, if you go back to the history of AI, has always been one of the big challenges for AI to build problem solvers that are not brittle. They can just solve one task, but they can cope with flexible and dynamic scenarios. But also from, again, going back in terms of cognitive science and common sense, the most important problem is that while we tend to learn concepts, if I learn the concept of a boat, then I tend to be pretty good at identifying every single type of boat in the universe. While the deep learning programs don't learn the concept of boat, they learn to recognize boats from their geometric and aesthetic features. Which means that if I design a boat which is completely different from any boat that has ever been designed, then that will be typically that will not be a problem for a human being, but will be a big problem for a deep learning system. In fact, again, just to keep you a little bit awake in case you are already asleep, the first one who tells me what this is, again, will get an acknowledgement from me in the chat. I will just leave it for another 3 seconds. 1, 2, 3, and then I'll move on to the, okay, which car? Can anybody recognize which? Yeah, well done to Rosalind and Mark. So I rest my case. You guys can recognize a Volkswagen Beetle even when this Volkswagen Beetle has become essentially a ball in some kind of art, exhibition, so for artistic purposes. Now, trust me, this will be much more difficult for a deep learning object recognition system, because the system will have never seen a beetle which looks like a ball. And the thing is that we are much better immediately identifying the key features of the concept we are talking about. So a car is something that normally has wheels. A car normally something that has a registration plate. So we understand conceptually the components of a car independently, as in this case, from the geometric layout. So again, well done to Mark and Sophie, and let's move on then. So as I say, for all these limitations, you cannot do object recognition. Well, let's say if you want to do state-of-the-art object recognition, that's what AI provides nowadays. The modern deep learning architectures. So we take that as a starting point, and we define, of course, a specific object recognition task in KMI, which includes essentially all the common objects you have in offices, like computers and sofas and doors and radiators and etc. And of course, you have people, you have robots, and of course, because we are a sort of funky bunch. We also have electric guitars and microphones and table football and all sort of great items that characterize a lab environment. And of course, because we are talking about health and safety scenario, it would be useful for Hans also to recognize, for example, health and safety signs like emergency exit, fire extinguishers. So this is the domain. And just to give you an idea of, this is from a video showing Hans going about his, investigation routines. Now, as you can see here on the top right, this is essentially what the perspective from Hans' point of view. And as you can see here, Hans is able to see that on the right-hand side there is a plant and recognize the plant correctly. But it's actually interesting because here there is these, there are these shells. There is this unit here, and of course Hans thinks is a box because from this perspective it looks like a box. Of course, the moment then Hans is next, is in front of the shell, it will be much easier for Hans to recognize this shell. So essentially, you can see how object recognition in the dynamic world is not just about one-shot image recognition, but it's also about looking at the same object from various perspectives and then being able to identify what is the this object looks like a box from one side and a unit, a shelf unit from the other side. Which one is the correct answer? Again, that requires a lot more knowledge than simply object recognition can give you. So of course, as a baseline, we started with what is considered the state of the art, in particular the Keynote, a sort of two-stream convolutional network developed by Zheng and other people only a few years ago. And essentially, I will I won't have time to give you all the details, but essentially the key number is the one that is highlighted here. Essentially, the performance is not that bad, but it's not that brilliant. It is only about 50% on instance base, which means basically for any given object, there is only 50% chance that the deep learning component will get the object right. So, of course, we want to do much better than that. So, so what we did, we looked at the kind of errors that the deep learning component made. So, and some of these errors are reasonably funny. So, for example, here you can see that the deep learning component correctly identifies the sofa here in this little sort of rest area that we have with sofas and chairs and armchairs and table football, etc. But this is an armchair, and the deep learning component thinks it's a mug. Now, of course, the shape of this armchair reminds a mug. So from a geometrical point of view, it's not necessarily a completely ridiculous, I would say, guess. But the reality is that no human being will make this mistake because we know, oops, hold on a sec. Sorry, we lost it. Because we know that typically MAG are not as big as that, unless we live in a land of cyclops. So again, the hypothesis that if our reasoner, knew a little bit about size, a little bit common sense knowledge about the size of objects, maybe we can improve the performance. An even more interesting case is this one where you have here on the right-hand side, you have this window. Of course, because the window reflects the blinds on the other side of the room, the object recognition system thinks it's a radiator, which again makes sense because radiators look a little bit like that. But at the same time, again, this is something that no human being will ever make, especially a human being who has been in KMI more than once, because depending on the light condition, you will not get that reflection. So in another routine patrol, Hans will have spotted that that is a window. And of course, if something is a window on a Monday, it's very unlikely that it becomes a radiator on a Tuesday. So again, from a common sense knowledge point of view, you see that this our deep learning system doesn't have knowledge about what we call the motion temporal properties of objects. windows don't move in general. It's very rare for a window to move, and certainly they don't change. They don't sort of become radiators over time. It's not impossible that a window is eventually replaced by a radiator, but it's a very unlikely phenomenon. So, so basically, we then develop a more precise research question that is, okay, the hypothesis that if we give Hans common sense knowledge, the performance will improve. And the research question then becomes, okay, what are the types of common sense knowledge we need, how we can represent them, and then how we integrate these with the deep learning module. So let's look at the first question first, that is the types of common sense knowledge we need for Hans. Now, again, there is a lot that can be said here, but essentially, if you look in the literature, both on the cognitive science literature and also specifically AI and common sense, there are certain components of visual intelligence that have been identified by various people. For example, obvious things, for example, that I mentioned earlier in the context of the example about the electric heater and the flammable paper, this idea of things being on top of one another, this kind of naive physics things, there are some amazing results from cognitive science that show that, children as young as 4 months already understand basic physics, and already understand essentially that if the window is there on Monday, it's unlikely that on Tuesday you have a radiator, or things like inertia. And of course, compositionality, we saw that in the example of the beetle. People are very good at processing objects in terms of the subparts and identifying the components and also spatial relations, which is a different case. But essentially, as I pointed out earlier, because we do it in a more conceptual way than simply looking at the organizational at the sort of geometric structure, the layout structure of objects. We understand that a car has wheels, even when that wheel is in a really funny place where it's not expected to be. The other important thing is, of course, again, there is a lot of evidence in the literature that we are very, our visual perception system is ridiculously fast. This fast perception element. There is also interesting work about these generic 2D views. We actually construct the 3D element mentally from prototypical 2D shapes. And this is again connected to the fast perception. And this allows us to very, very quickly to recognize objects, but also in evolutionary terms, for example, in recognizing danger, recognize a sort of dangerous animal from a non-dangerous animal. And then finally, this is what I mentioned earlier, this motion vision, this ability to maintain distinct representation for static and moving objects. So how do we then go from these, I would say, more high-level cognitive science framework to a concrete operational framework? So essentially, what we did, we sort of instantiated these generic components into specific I would say, specific AI components that we feel we can implement in the Hans architecture. So naive physics essentially is about understanding the physical properties of objects, like nodal orientation or size. Compositionality is about equipping Hans with spatial reasoning, path-forward relations, etc. Fast perception is really what DL methods does. On known categories, we can really identify objects very quickly. The generic 2D views is, for example, using the generic 2D shapes that are provided by KBs like ShapeNet. And the motion vision is essentially by allowing Hans to do action recognition, object tracking across time. So in particular, if we do a more fine-grained error analysis, we can see that some of these components seem to be, at least in principle, seems to be more useful than others to try and correct the kind of problems that, well, let's say, correct the kind of errors that the deep learning component makes. In particular, we hypothesize that up to 74% of errors encountered by deep learning components can be solved with intuitive physics. in particular with the size, with the relative size, but also there are things like natural orientation. For example, a coat hanger is always much taller than wider. So if something is wider than tall, is more wide than it is tall, then it's very unlikely to be a coat hanger unless some designer really came up with a completely new coat hanger. So relative size seems to be a really useful thing to try and give to hands. Of course, also this ability to do qualitative spatial reasoning seems to be very useful. And also these things about the motion trajectories also seems to be very useful. Another thing also that was not mentioned in the framework is the machine reading components. Actually, the ability to read the signs like, emergency exit signs, or sometimes like you have a recycling bin, something that, for example, that is used as a recycling bin, and they just put the label recycling bin. So that has to do with affordances object. So sometimes objects play a different role from the one they've been designed for, but that role, for example, can be simply identified by reading the label on the object. So machine reading seems to be very useful. So basically, we added the machine reading as another capability that we want hands to have. I'll skip this. We also did an analysis of, to what extent these knowledge requirements for visual intelligence are covered by existing knowledge bases. But I will just, invite you to read the paper and, find out more about what is lacking currently in existing resources. So what we did. So first thing, let's introduce a size reasoner. Essentially, the idea of the size reasoner is linked to this. Also typicality and plausible reasoning. I expect a mug to be of a certain size. If if I see an object which is 5 times the size of a typical mug, that is unlikely to be. It's not impossible, it is unlikely to be a mug. And this is again connected to, for example, the work by Roche on our ability to categorize objects in terms of stereotypical features. So what we did, we collected dimensions, object dimensions for the objects in KMI from a variety of sources, in particular Amazon, but also ShapeNet. We did a little bit of cleaning to remove errors, and then what did we did? We sort of squeeze it into a 2D sort of area in depth. Also because that makes recognition faster, but also because typically it's much more difficult for hands to identify, to determine the depth of objects. So it is important, while it is easier to determine the area. So it's actually quite useful from a computational point of view. If instead of having a 3D representation, we have a 2D representation. Another thing also, we sorted them into a sort of two-dimensional space to do with thickness versus size. And an important thing, this is really the important point to make. You can have, for example, the concept of a box. By box can be really big, as up here, but also a box can be both small and completely flat because it's been folded. So again, in an image recognition problem, typically, these two will be two different objects. In the case of hands, it would be nice if Hans was able to recognize, well, this is a cardboard box, this is a big cardboard box, and this is a small cardboard box, this is flat, this is not flat. And this is both in terms of performance, but also in terms of explainability. So how we did with the integration, how we integrate the size reason with the deep learning component, we did it in the kind of obvious way. We used, which is actually has some advantage. We used essentially this waterfall model in which first you have the object, the deep learning component. The deep learning component makes a guess, provides a prediction, but of course the deep learning component also is able to give a confidence score together with the prediction. So essentially what we do is that if the confidence score is below a certain threshold, which is actually determined automatically, then the size reasoner kicks in and looks, essentially using the image, both the two-dimensional images, but also the depth information, tries to confirm what the object, what the deep learning component has produced. You basically say, well, does this make sense from a size point of view? So, for example, like if in this case we have a fire extinguisher which has been confused for a bottle. If the size reason says, no, this fire extinguisher is too big to be a fire extinguisher, and if bottle is also one of the possibilities that is provided by the deep learning component, then the size reasoner will change the ranking and will say, it's much more likely to be a bottle than a fire extinguisher, because this is a fire extinguisher. Bottles normally are not so big. So, and by the way, one important thing, because we have had a few problems with some reviewers which didn't like this waterfall model, in which first you have a deep learning component and then you have the size reasoner. And we think actually this has a number of advantages, in particular the modularity. Of course, you can go inside the deep learning component, try to get size in the learning algorithm, which is actually not completely trivial, but it's not impossible. But that means that you have to do it for every machine learning component, while this allows us essentially to completely separate the two elements, which also allow us to understand exactly what is the performance of the deep learning component, what is the performance of the deep learning component with the size reasoner. So we think is much better in terms of modularity and also explanation. But not all reviewers agree with our point. So just to remind you, the performance of the neural network reasoner was about 50%. What we found was that if we use all the information at our disposable, area thickness, and also aspect ratio, things that are taller than wider or wider than taller, we increase to 55%. Which is a good result, in a sense. We already pushing. Essentially, this demonstrates that if you add the common sense reasoning component, that helps. But unfortunately, it's not as good as the theoretical result. By looking at essentially, if instead of having automatic threshold identification mechanism, we had a sort of magic oracle. Essentially. The ground truth, oracle that tells you that every time the deep learning component makes a mistake, kicks in automatically the size reasoner components, then the overall performance will be 66%, will be a very, very significant improvement. So that means that there is still some interesting work that can be done on trying to understand when to kick in the size reasoner. Essentially, what we found is that with the current architecture, sometimes the deep learning component is kind of overconfident about a prediction that turns out to be incorrect, and therefore the size reasoner doesn't kick in. But at the same time, what we find is that if we allow the size reasoner to kick in every single time, because the size reasoner itself can make mistake about determining the size of the object in the real world, then sometimes it will overrule correct predictions from the machine learning component. So there is essentially an open problem how we can push the 0.55 to 0.66 with the architecture which does not rely on a magical oracle that tells you when the machine learning component gets it wrong. More interestingly, if we take one of what I call slightly, a little bit more artificial, or at least more, let's say, well-behaved test case like the Amazon Robotics challenge, then really, we can use our size reasoning together with a combination of NNet and KNet. NNet is a machine learning algorithm, deep learning algorithm that is best for known objects. KNet is one that is best for known objects. We actually push the overall performance of the hybrid architecture to 88%, which is a significant improvement of the two components taken individually. Okay, so I understand I still have 5 minutes to go. If I don't, please shout. Organizers, please shout. So I'll use the 5 minutes to tell you about the second component, which I've added to the architecture to try and improve the performance even more, which is essentially a spatial reasoner. You know, the idea here is that when you want to make sense of the environment in front of you, you know, you need to understand relations like, you know, right off, left off, above, under, near, in front of, behind, etc. And again, interestingly, in the community, there is a little bit of a split between you know, the classic AI work on spatial reasoning that is based primarily on formal models or queries of these relations on formal logical theories, while of course in the robotic community is much more about essentially try to identify objects and then using semantic mapping to represent the knowledge for the robot. So what we did in our work is to try to bring together these two worlds to build a concrete component that is able to equip Hans with the spatial reasoning capability to improve his performance in object recognition. So, okay, I already say that. Another, yeah, just one more thing. The other thing, of course, that is interesting is that the language we use tends to be informal. For example, we can say A is on B, both in a case in which something like this mug. Hello? Sorry, there was something, somebody stepped in. And also on when something is affixed. And again, from a point of view of spatial reasoning, these are two different situations. Here is something which is not really on the wall, in the sense it's not on top of the wall, it's affixed to the wall, while this is something that is on top of a couple. Okay, so I will go very quickly on these. Oh, sorry, there should be a, yeah. If you want to know all the details, I suggest you read, we have a preprint on archive, Common Sense Spatial Reasoning for Visually Intelligent Agents. But essentially the key thing to point out is that, so we, in good AI fashion, we produce a very beautiful logical theory with about 40 axioms, which essentially builds on the notion of geometric point and proper spatial region. It is a spatial region which is a connected set of geometric points, which is what is of interest when you try to identify an object. But the really interesting thing that I would like to highlight here is that, of course, object, you know, when you have spatial relations and spatial region, you need to have a frame of reference. And the interesting thing again in the real world is that the frame of reference is very dynamic, because we want to have a frame of reference which is aligned with the frame of reference of the robot. So this was something that was not really covered very well in the existing literature. So we did a little bit of formal work and came up with the notion of contextualized bounding box, which essentially means given any object in the world, essentially the system is able to produce what is called the minimum bounding box, that is the small box that essentially completely contains the object. And that is always with respect to some frame of reference, for example, can be an absolute frame of reference that you have in the environment. The contextualized bounding box is essentially about taking the minimum bounding box for an object that we have identified in the world and rotating so that it becomes aligned with the frame of reference with the robot. This is interesting from a formal point of view, but also is very important from an engineering point of view to allow Hans to improve his object recognition capability. So in practice, what does this mean? Just to make it more concrete. So Hans will see a situation like this with a bin, fire extinguisher, radiator, fire assembly sign, etc. And he will automatically construct this bounding box associated with the objects. And then he will also construct a logical representation, which says, something, the sign is above the fire extinguisher. The fire extinguisher is affixed on the wall, while the fire extinguisher number 2 is leaning on the wall, is not affixed, etc. So essentially, is the ability to go from an image to a geometric representation in terms of contextualized bounding box to a logical representation in terms of spatial relations. And of course, the interesting thing about spatial relations is that, from a common sense point of view, is that, certain objects make sense, a keyboard makes sense next to a mouse. So let's say a mouse makes sense next to a keyboard. So if I identify a keyboard and the object next to the keyboard is unclear, but it may be a mouse, well, there is a very good likelihood in terms of typicality that that would be a mouse, because typically in my experience, mouse and keyboard tend to go together. So we use this typicality, and we train these both on the spatial relations we found in KMI, but also on the visual genome KB to give us a much larger set of a much larger knowledge base on typicality. So we integrated the spatial reasoner with the architecture, and essentially now there's still this waterfall, but essentially now the architecture is a bit different. Essentially, you get the prediction from the planner, and then basically both the size reasoner and the spatial reasoner provide their own evidence, or make their own suggestions about which would be the right ranking. And then there is essentially a majority vote. That is, if the size reasoner says that it's most likely to be a bottle rather than a fire extinguisher, while the deep learning says no, I think it's a fire extinguisher, and the spatial reasoner say, yeah, that makes sense to the fire extinguisher because it's under the sign fire extinguisher. Funny enough, then it's a fire extinguisher because two components overrule the size reasoner. So that's what we did. And again, I remind you the results when we were with the size reasoner and the DL were 55. And we did all sorts of experiments again with oracles, etc. But the important one is really the real world, where you really have no information about what is wrong and what is not wrong. And this was again, it proves the point that more common sense knowledge push performance even more. However, we went up from 55 to 58, which is, not as good as we would like to be, which again points to the need to do a little bit more work on trying to get these multi-component, this kind of knowledge fusion for decision making more intelligent. Okay, so I think that's all I have to say. Sorry for being a few minutes over time, but essentially the key point to take home is, yeah, deep learning is great, and nowadays these object recognition systems based on neural networks are quite impressive. However, they are less impressive in the real world, and in the real world it makes sense to use common sense and to try and get our robots to be a little bit less brittle and understand more about the world they operate in. This is in a sense, from a point of view, AI and the AI paradigm, I think this is a nice example in which, if you get different AI paradigms together, you improve over a single paradigm. But of course, there is much more work that is needed, more on adding more common sense knowledge to hands, but also, as I said earlier, to work a little bit more in detail on the meta reasoning element architecture to be more effective in combining these different sources of knowledge and therefore decision making. Okay, that's all for me. Thank you much for listening.
Thank you, Enrico, very much for this marvelous talk. It was very, very interesting. And I think you once again showed how hard it is to tackle these problems that you're working on. We now have 10 minutes left for questions. Are there any questions in the audience?
Well, thanks for the great talk. I was just wondering, as I looked at the scores, as the recall was way lower than the precision, does that mean that your model has generally problems to detect a 3D object itself?
Are you looking at this case, or in general?
This case, yes.
Can you repeat the question, please?
There's a slight difference between the recall and the precision. As you can see in the scores, you have 58% F1 score.
Yeah.
54% recall and 71% precision, which would mean there might be a lag in even detecting any 3D object. Is this correct in this case?
Yeah, no, you're absolutely right. I mean, essentially, there are two. Well, I would say the key point here is that the architecture is quite conservative. That is, you know, we use we rely on the deep learning algorithm for confidence, and indeed the deep learning algorithm tends to be quite good at confidence in many cases, and then the size, the other two components essentially act as correctors. So it's a little bit of a skew, you know, although it's a three-way decision-making process, is a little bit skewed in favor of the deep learner. And the problem is that because there are different types of objects and there are different conditions, you get in fact, yeah, if you look at for example, the class-based, so essentially there are certain categories of objects that tend to be much more tricky to detect it. And those are the ones, for example, where, you know, like boxes which can have different forms, and all the ones, for example, like the case of the window, the radiator, where you need these motion vision component, which we have not implemented. So in a sense, the fact that we have a better precision than recall is a little bit to do with the approach. You know, essentially incrementally, we try to get better and better, which means that we keep as good a precision as possible. We try to improve recall over time, which is a feature, I would say, of the specific scenario in which we are working and the specific architecture we are using.
Thank you. Another question over there.
Thank you for your talk. When you spoke about the limitations of AI, the first on your list was hungry data. And I was just wondering if you have distinctions about what sort of data and any priorities about that. For example, would automatically generated data, how would that be compared to human created or curated data, or any convergence of these or any of them? Thank you.
Yeah, this is a great question. I think there are two aspects. So one aspect is simply data. You know, these certainly, you know, modern machine learning algorithms, they can achieve almost any level of performance, including 100%, as long as you give them complete data, and then things don't change. You know, you have a reasonably static world. So in general, of course, you can simply throw more data at a problem, and you will improve it until then you get overfitting, and then you get this problem that, you know, becomes even more brittle than before. So on a more generic sense, I think the problem is you know, is a little bit, you know, as shown in this slide with we looked at the, you know, these knowledge requirements, and then we look at the knowledge base that are available. There are certain types of knowledge that are not very well covered in knowledge bases, including, you know, knowledge base like ConceptNet that should be common sense knowledge base, or WebChild that is really designed for common sense. So, for example, you know, one thing that we discover with Hans is how important is notion about motion trajectories. No, this is what I call this sort of temporal motion element. You know, the fact that there are objects that are very mobile, like human beings are very mobile, and there are things like a window or a radiator which is you know, has been, you know, plumbed on the wall, that are not mobile at all. Now, this is something that, as I said, you know, babies can learn very quickly. at very, very young age. AI systems don't have this knowledge, and this knowledge is not, is hardly present in any knowledge base in the world, including common sense knowledge base. So it's a multifaceted problem. Is about building knowledge base that cover more of the type of knowledge that we are able to use to operate in the real world, as well as, generally speaking, having more data to throw at the problems.
Another question?
Thank you for the talk. Could some of the output of the knowledge base reasoner be used to make like an action the robot could do to collect the most useful data to run the next time? So you could go somewhere to have a hypothesis about, if this is a cup, then if I go there, then it should become smaller or something like that.
Yeah, indeed. No, that's great. Indeed, this is something that we have started doing, and as I said, in my conclusion, one of the next priorities is to add these essentially these motion, these properties about motion, special motion properties, as we call them, or temporal motion properties. The properties of certain objects to move or not move. So the idea is that over time, Hans will build more and more of his own common sense knowledge base acquired from experience. And then this can also feed in as a generic source, for example, to augment things like visual genome or other knowledge base. So yeah, that's exactly. And what would be great, of course, is in 5 years' time, when there are lots and lots of robots going around doing interesting tasks, if the knowledge they acquire, the same way we acquire knowledge over time, we become better, and then we share this knowledge, like in conferences. Robots could do the same thing. So you can imagine that essentially robots as dynamic sensors could, in fact, could go beyond being dynamic sensors and being sort of dynamic knowledge-based constructors, in particular for common sense, typicality kind of reasoning.
We have room for one more question.
Thank you. Very interesting presentation. I was wondering how your framework would deal with completely new types of objects. So, for example, in your lab, there is suddenly someone brings their child there for daycare, and there is a toy. And how would Hans? You do not have any statistics about where it typically is located or what its properties are. How would you deal with this?
Yeah, again, this is a great question. We basically, if you don't know anything, you cannot identify anything. Yeah. So if a toy object which has never been seen before appears, Hans will have no clue. But again, this has to do with the background knowledge. If you have enough background knowledge, and you can, for example, let me make a slightly simpler example, which is that of table football. If you have a good representation of tables, and the table football appears, and you have never seen a table football, at the very least, you should be able to understand that that's a table. Yeah. Then how you get from a table to table football is a bit more complicated, because you have to have knowledge about what happens in the world. So I would say the answer is two ways. First of all, more sophisticated taxonomies of objects that allow maybe the researcher to identify an object maybe in a more generic way, not exactly at the right, at the precise level of abstraction, but maybe in terms of a more abstract class, number one. And number two, of course, the moment the knowledge that we provide to Hans, the moment, for example, the visual genome database becomes so comprehensive that any object in the universe is covered, or the moment, for example, that the entire Amazon catalog is fed to Hans, then most objects will not be completely novel. Most objects will be novel to Hans, but maybe Hans will be able in the Amazon catalog to spot a toy which is the same one as the one that appeared in KMI, or very similar. So I think again is to do with having more knowledge and more data fed into the system, and more sophisticated representation.
So I think we have finally reached the end of the keynote. So give again warm hands to Enrico for his great talk. Enrico, thank you very much.
Thank you. Thank you very much.
I am not completely sure if you can see me, but we have a little present for you, which I now and here hand over to you virtually, and it will be sent to you by postal service. Yes. So thank you very much again.
Thank you very much for the visual present. I do appreciate it. Thanks a lot.
Thanks a lot. And we go into the break for half an hour, I think. Or can you correct? Is it 15 minutes? 15 minutes, and then we continue with the regular talks. Thank you very much. Thank you, Enrico.
Thank you very much. It's been great fun, actually. And
Quando a gente vai embora, bota o pé no mundo afora. Toda a vida se balança que nem uma linda menina de trança que vem pra avenida samba. Quando a gente vai se embora, levando esse mundo afora. Toda alma chora tanto, não tem coração pra entender esse tanto e nem bota essa alma pra samba. Quando a gente